Okay, I reckon you can begin.
All right. So, what have we seen so far in the seminar series? We saw what I'm going to call, my pen is always too small. I'm going to call classical crypto, which is essentially this setting where we define games and say that no one can win them. No adversary can win them. So that was what we spent most of the first seminar discussing. And then we saw simulation cryptography, or simulation security, if you like, where the idea is that you can't tell apart a real world and an ideal one. And we kept the discussion fairly imprecise and vague, mostly because the first ways that we try to approach these things turn out not to work for slightly subtle theoretical reasons. So today we are going to start finally building the theory of universal composability. And we're still not going to get extremely precise. I'm not going to state any really crunchy definitions yet, because we have to understand the idea behind how we're going to build this before I really just go and dump the definition of an interactive machine on you. This will be way too much. So we're going to spend a while understanding what exactly we're going to build and how we're going to build this. Okay, so the idea behind this simulation security notion, to recap, is that we have, I'm going to draw this as some box. It's a protocol that several parties can interact with. I've got party 1 here, party 2 here, and there's also an adversary, which I'll write as A, that is going to interact with this protocol. This is the real world here. And on the other hand, we have the ideal world. And this represents a perfectly secure scenario that definitely does what we wanted to do. So last week I used the example of a secure channel. Party 1 wants to send a message to party 2 in such a way that the adversary cannot read it, and the adversary also cannot fake messages. So an example of the ideal world here would be that the system simply writes the message to party 2, and the adversary sees completely random noise coming out. Random noise that has no correlation with the actual message. And we introduced the idea of a simulator. So the idea behind the simulator is somehow there has to be a way. If someone physically taps my wires, even if I have a perfectly secure protocol, they still see something. They just don't learn anything. So the simulator is here to act like the adversary that can't achieve anything. And we said that the idea is anything the adversary could do in the real world could also be done in the ideal world. And to make that a little more concrete, I'd like us to picture an environment. This environment is also going to be eventually an interactive Turing machine. And the environment's job is it provides input to each of the parties. And it interacts with the adversary. It receives some output from the adversary. And the idea is that the environment wants to distinguish, it wants to tell whether it was interacting with the ideal or the real world. So you can view the adversary as trying to provoke bad behavior. And it's the environment's task to try to tell the difference between them or to distinguish the two worlds. So the adversary tries to provoke bad behavior. And the example of a message, a bad behavior might be sending a message that was never input, right? If party 2 receives a message that party 1 never sent, that's bad behavior. So the adversary is trying to provoke this, and the environment is somehow trying to detect it. And we said that if for every adversary there is a simulator that can do the same thing in a perfect world, such that the environment can't tell them apart, then we will decide that this protocol is secure. And we saw an example where this breaks down in a parallel, in a concurrent context. So if we try to execute the same thing twice in an interleaved fashion, we saw last seminar, we saw how this completely breaks down the security guarantee. It reveals things that it shouldn't. And this is related to the fact that the environment somehow only interacts once. First, it gives inputs to the parties. Second, it receives outputs from the adversaries and the parties. So while the protocol is executing, whatever's happening inside this protocol, the environment has no access to. So we can't model scenarios where perhaps multiple protocols are interacting with each other. And so we have to go to a more general context. We're going to see how we're going to build up all of this. Somehow it's clear that we need a few things. I'll have to go to the next board to start discussing. So what do we need in order to actually make this mathematics instead of a lovely story that we're telling? Well, the first thing we need is some notion of a machine. Okay, and because we're computer scientists and are not terribly creative, this is going to be a Turing machine. You could, in principle, build this out of a random access machine or some other computational model, but I'm following the universal composability paper, which builds it out of a Turing machine, largely because this is how they know how to do it, right? So I need some notion of a machine, and that's going to represent each party, the adversary, and the environment. So all of these things are machines. And just to recap, the parties are sort of innocent. The adversary is trying to provoke bad behavior. And the environment is trying to detect the bad behavior. Because if it can see bad behavior, it must be in the real world, because the ideal world cannot have bad behavior. So these are the three key pieces that we're going to build into machines. Second thing that we need is some notion of a protocol. So somehow it's an ensemble of machines that makes sense, right? They obey some kind of coherence criteria. Because if we just have a bunch of machines that are not talking to each other, or perhaps one machine can talk to one in sort of this complicated, confusing way, it's not going to make sense. So we're going to have some criteria for what we want to think of as a protocol. And once we have defined those pieces, we have to decide what the execution semantics are. So how does the protocol run? Who starts? Who sends what to what? What is this mathematically? What are the correct objects? So to define the semantics is what we're going to do after we know what a protocol is. In other words, how does this execute? What are the inputs? What are the outputs? How does this all look? And the fourth piece is a notion of emulation. So the idea is I want to emulate a fancier protocol using a simpler one. So I want to build a more secure system with weaker assumptions. A classic example of this is the TLS protocol that we use in HTTPS. All I start with is a certificate, like a signing key pair. And the TLS protocol uses key agreement, authenticated key exchange, a few other bits and pieces, and builds a secure channel just based on the certificate that's stored in your computer and some standard computational assumptions. So that's this notion of emulation. And we want to say our system is secure if it correctly emulates the target specification. Okay. So let's start interrogating these pieces. I'm not going to define a machine fully yet. I'm going to say that it has to do certain things, but I'm not going to say exactly what it is because I'll come back to that next week when we really get into more formal definitions. But a machine is going to have at least these parts. It needs an identity. So you can think of this as just a number, if you like. We're going to call our machine mu because we are very creative. So the identity is, if you like, it's an element of the natural numbers, but the choice of the set, of course, is arbitrary. And it's visible to mu. So whatever computational model we're using, it can somehow know what its identity is. And it's got to be constant. So throughout the whole execution, the identity cannot change. One reason we're going to need this is so that we can define a communication model. If a machine is to send a message to another machine, it needs to know which machine to send it to. If that identity is not constant, we are going to run into problems. So another thing that it needs is types of communication tapes. One way that you might think to define an interactive Turing machine is it has an extra tape, a communication tape. Messages are written to this tape, and an instruction that the Turing machine can execute is to read a message from the communication tape. One tape is not going to be enough. Intuitively, this is because the adversary, in some cases, needs to use a backdoor manner. So if we imagine a multi-party scenario where some of the parties are corrupted by the adversary, just writing it onto the communication tape publicly is going to cause problems. So we have 3 classes of interaction tapes. There's input. So for example, the environment will pass input to each of the parties. There is subroutine output, which is an unwieldy name, but it corresponds pretty naturally to the idea of subroutines in computing. And the idea is, if some machine gives me input, then at some point I will give it subroutine output. These will end up on different tapes, mostly for the sake of modeling so that we don't have to include tags to say what kind of message it is, maybe read ahead on the tape. If we separate these into separate tapes, this will make modeling simpler. And the last kind is backdoor, which comes from it comes from the adversary. I run out of space. Okay, and the last thing that we need is what we're going to call a communication set. And essentially, not every party can communicate with every other party.
Sorry, Eleanor, can
Yes?
you reiterate? I mean, I'm pretty used to interleaving multiple tapes on single tapes and such things. So can you repeat what the essential distinctions are? I mean, you outlined how these different tapes will be used, but
yes,
they must have somehow different properties or different constraints. So, for example, is the input tape, is that like read-only to a machine? Or how is it limited in terms of how it uses these tapes, or how the environment or adversaries use these tapes?
Yep. So we're jumping ahead a bit, but that's no big problem.
Oh, okay.
These are essentially, this is set up to make things simpler. We could interleave multiple messages, as you say. The formalism that we use does not do this. I guess simply to avoid messing around with bits and pieces. And it says, well, you know, we don't have to worry about this. So we don't have to be efficient somehow, right? We don't have to use the minimal amount of space, so we're not going to. One case where the distinction will turn out to be relevant is defining polynomial timeness. This is, again, jumping ahead a bit, but the essential problem is if I have even two interactive Turing machines that are on their own polynomial time, then their interaction may not be polynomial time because they could just send messages back and forth. So we need some way to model this. And the way we're ultimately going to do it is that machines have a resource, some kind of token, and they provide tokens on this input tape, and this limits somehow what the Turing machine is able to do. It can't do an arbitrary amount of stuff. It uses up these tokens. So this is one way, right? This is one way that we can do it. This is one reason that we want to separate these, rather. Also, for the backdoor tape, it becomes easier to reason about what different machines know if we separate out information that is not public in some sense. I think, Dan, you sort of raise an important point that this choice is kind of arbitrary, right? We could interleave them. We don't need to separate them like this. The theory has a lot of these arbitrary choices, and it's not just you. This is somehow a modeling artifact, and it's symptomatic of cryptography being a young discipline. Even if we consider how long we've had ciphers that were actually good, the earliest we have the one-time pad in like generously about 1900, which is the first cipher that is actually good. So cryptography hasn't been around that long as a serious discipline. And modern cryptography, where we're really thinking about multi-party protocols, computational assumptions, is even younger. So we kind of have this arbitrariness, this clunkiness. I think this is really symptomatic of the fact that it's a young discipline. Yeah.
Cool.
Maybe I think you're right to raise some eyebrows. My goal here is really to present the theory as it stands, right?
Mm-hmm. I can also be patient, so yeah, thanks.
Yeah, no worries. Okay, so we've got these interaction tapes, and now we want to say parties can't talk to every other party. In particular, we could have a secure channel just come out of thin air if party 1 could just write directly to party 2's tape, right? That would just, suddenly we have a trivial secure channel. So we also have a communication set, and that says what machines can each party, what other machines can each machine interact with? So it just says which identities mu can send to, and also which tapes. So we see again this distinction between the tapes. We might allow some writing to one tape but not another, and we will see that this allows us to avoid some silly trivialities. So I move on to the next slide, and the next board, I have an example to make this a little bit more concrete. So let's say that I have a machine with mu1, it has an identity 1, and a communication set that says I can provide, input to machine 2. And then mu2 says, I'm machine ID 2, and I can provide output to machine 1. So this is a secure channel because mu1 can write directly to mu2. And in practice, we can't construct this, but we can construct something arbitrarily close to it. And as we will also see, every machine has backdoor permissions with the adversary. This might raise an eyebrow. Are we saying that every machine now is colluding with the adversary? I'll write A for the adversary's ID. And the answer is, well, we will restrict our attention to adversaries that, in some sense, behave, right? We will say the environment which is orchestrating this, is ultimately going to orchestrate these interactions, will not allow the adversary to take over any machine it likes. And you might ask, why are we restricting the adversary? Surely we want to capture anything an adversary could do. And I might answer, yes, that's a good point, and not comment further. We'll see that to model this, to really build this model, we're going to have to make some simplifying assumptions. And a lot of this comes down to what exactly we allow each type of machine to do. And this appears in the model, but not in the real systems that we try to capture. Okay. So a machine then is an ID, a communication set, oops, and one more piece, the code, if you like. So this code somehow represents what the machine does, and I'm going to represent it with the tilde. And if you like, you could say this is the formal Turing machine, the tuple of the alphabet, the states, and so on. And it represents what the machine can actually do. The reason that we include this in our collection of what a machine is because sometimes we might want to look up a machine by property. You might want to say, I'm sending a message to all machines that do this. And if we define things very carefully, we will avoid Rice's theorem. The classic result that you can't decide semantic properties of programs. We can avoid this by being very careful, and that's why we include the code in the machine definition. Okay. So my first real definition is a machine. Whoops. A machine is a triple mu. The first element is the ID. The second element is the communication set. The third element is some kind of code of the program. Identity. C is the com set, which, if you like, is for each natural number, I have either input, subroutine output, or backdoor. It's an element of this, I should say, not equal to. And mu tilde is the program, which again, you could think of as a formal Turing machine. So the picture that we have here of what a machine is, some box, it has an identity, it contains some code, it has backdoor communication for the adversary, it can provide input to other machines, it can receive output from other machines, And similarly, it can provide output to other machines. And it can receive input from other machines. Okay, so this is what a machine is. It's any concrete realization that satisfies a structure like this. Okay, I'm going to go back to the first board. Okay, now we're going to define protocols. So to discuss protocols, we're going to look at the different ways machines can be related, and we're going to define coherence properties. In particular, if A provides input to B, then B must be able to provide output to A. So the definition of a protocol is going to make sure that these links are correctly made. So these possible relationships come in 3 types. So for a set of machines, mu1, mu-n, and each mu-i looks like this. It's a triple IDI, communication set I, program I. We say that mu-i is, it's a caller of mu-j if it can provide input to mu-j. Okay, so it can call, we call it like a function, meaning we give it input. It's a subroutine of mu-j if it can provide output to idj. And it's a subsidiary of mu-j if it's a subroutine or if it's a subroutine of something that is itself a subsidiary. So we're just doing a transitive closure and calling that a subsidiary. Subroutine of mu-j or another subsidiary. So we have some picture like this. Yes?
I'm a bit confused. So mu-i can be a subroutine of mu-j. That means mu-j can actually supply output to. Oh, sorry,
Supply
I missed what ci
input.
and ei were.
Oh, this is
Right.
sorry. This is a board artifact. Yeah. So it's a caller if it can provide input to mu-j. It's a subroutine if it can provide subroutine output to mu-j. And it's a subsidiary if it's a subroutine. Sorry, yeah.
How does mu-j, I mean, can I provide input to mu-j in that case? Or it's supposed
In
to
the
like
subroutine
first get
case?
the input? Yeah. I mean,
Yeah, the idea, so what we'll do...
subroutine seems like a two-way thing, not a
precisely.
one way.
So the definition for protocol says it forms a protocol when you have this closure going on.
I see.
Otherwise, it's not a valid protocol. If mu-i is a subroutine of mu-j, but mu-j can't give input, we say it's not a protocol.
Okay.
So just for those of the viewers who might be a little more visual, we have some kind of graph structure going on, right? So if mu-i is a caller of mu-j, and, sorry, if mu1, I should make this, if mu1 is a caller of mu2, that looks terrible, let's not use that color. Mu2 might be a subroutine of mu1. Similarly, mu3 might be a subroutine of mu2. And same with mu4. And the idea, what's a subsidiary? All of these nodes here are subsidiaries of mu1. And if we want it to form a protocol, then we also have to have this two-way relationship. Okay. So a protocol is a set of machines that satisfies this coherence property that Dan mentions. So a tuple, I will call a protocol pi, because it starts with P and I'm very creative. It's a protocol if every mu I that is a caller of mu j I should say for every, then mu j is also a subroutine of mu I, and for every mu I that, underline caller because that will be important in a sec, that is a subroutine of an identity, not necessarily a machine, identity IDJ, if some mu j has identity IDJ. So if there's if this is a subroutine, if our machine is a subroutine of some identity and our protocol includes that machine, then it has to be a subroutine of that machine and not some other machine. So the reason that we're defining it this way is because protocols can have machines that are subroutines of external machines. That's how the environment is supposed to provide input to a protocol, right? In order to receive input, it has to be able to give, in order to be able to give output to the environment, it has to be a subroutine of an external identity. So it's not a two-way relationship, right? If A is a caller of B, then B is a subroutine of A. But if your machine is a subroutine of some identity, it may not be in the protocol. So the second condition is saying we somehow can't have an identity that is in the protocol yet doesn't have this closure. But we can have an identity that's not in the protocol, that's fine. So if there's no mu j, if there's no such mu j that has the identity IDJ, we say that mu I is a main machine. You can think of this like in C programming, right? This is an entry point. So it's a main machine of pi. And the external identity in question is an external identity. So in this picture that I have here, mu1 might be a subroutine of ID E for the environment. But this is not a machine that's in the protocol. It's just an identity. It's an external identity that's floating in the ether. And then mu1 becomes a main machine. Questions, Dan?
I think I'm processing.
The idea is that a protocol can be called externally, perhaps by the environment, for example. And our coherence condition says that essentially we don't want these identities to collide, right? We don't want the identity that our main machine binds with to also happen to be an identity in the protocol. That would just break down the definitions. So this is sort of, it's a lot of mechanics that are going into the pot. But the idea is simply that we want to be able to call a protocol externally, and we don't want to have to worry about, oh, what if the identity clashes? We're just defining that out of existence.
Yeah, I think I have to see this in use somehow, or at least its role in a proof to really understand why things are set up the way they are. I think
Yes.
I find this use of the word subroutine pretty confusing.
I would agree with this.
But I guess I can get over it. But yeah, I mean, I think I'm struggling a bit with this last point about main machine and so on, but I think the rest of it makes sense. Yeah.
Right. So my hope is that when I define the execution semantics, this will be a little bit clearer. Yeah.
Could you repeat what the purpose of having something called a main machine is?
So I don't have this picture anymore, but what's going to happen when we define the semantics, the environment is going to run first, and it's going to give input to the protocol. If the environment gives input to the protocol has to be able to receive that input, right? Now the environment is a machine, so it has an identity. So the protocol needs to be able to receive input from outside the protocol. And the machines that receive that input from the environment are called main machines.
Okay.
You can think of it like, it's essentially modeled after a C-like programming language, right? What's the first thing that happens? The operating system calls the main function. Then anything else that happens inside the program calls a subroutine back and forth internally. And then at the end, the program finishes and hands its output to the operating system. So if you think of the environment as the operating system and the main machine as the entry point of the program, maybe that makes more sense. I'm not sure.
Somehow I did not even make this connection to main in a C program. Yeah, that helps.
Yeah. That's I think that's why these things are named the way they are. That's my interpretation of the theory. Okay,
cool.
So I'm going to define the semantics now. And the semantics are not going to be, again, not yet at the level of interactive Turing machines. We will get there, I promise. But first we want to understand how this dance is going to go about before we really get into crunchy technical details. So I'm going to write definition. This is kind of in air quotes. This is not really a definition, but it's close enough. So an execution. So we've got machines, we've got protocols. Now we need a notion of execution of some protocol, pi, with environment E. Remember, the environment is some machine. So I'm quantifying over the choices of environment here. And adversary, which is also a machine, A, on initial input Z. So we have a third quantification sneaking in. The idea is that the environment sort of receives this value Z from the ether, and then it executes the protocol with the adversary doing whatever it's trying to do. And we're ultimately going to say, no matter which initial input is given, you can't provoke the bad behavior. Why do we need this initial input? Well, for example, if you're trying to decide if a messaging channel is secure, then you don't want to require the message to be chosen randomly. So the message needs to appear from somewhere. The environment can't choose it because it would have to do so either always the same message or always randomly. So if you're modeling a secure channel, this initial input could be the message that is being sent. That's just one example. So it begins by running E on Z. And a detail that we'll see when I define the computational model next week is these interactive machines can, if you like, yield control. That doesn't mean they halt. It means they're saying, I'm going to stop now and hand it over to another machine. So the environment is going to take Z, do something with it, and then hand it as input to the protocol. That's the idea here. So the machines are going to take turns, not of their own volition, but because there's execution semantics demand it. So when some machine mu, which I'm going to expand into a tuple here, executes the transmit to identity prime. When I say executes here, I mean you have a typical Turing machine where the instructions are either write to cell, move left, move right, right? This is another instruction that our model is going to have. Say, transmit this data to this identity. This is going to be another primitive model. Once it executes this instruction, the machine is suspended. This is not a technical term, it's just a concept. Then, what happens next? Well, it depends on what the machine was. So if the machine that's transmitting a message is the environment, we write the message.
I'm sorry, I lost you.
Yes?
What's ID prime?
It's so the machine runs until it executes a transmit to some identity instruction. ID prime is capturing whatever identity we're sending to.
Oh, okay. So it's suspended anytime it attempts to transmit something to anybody.
Yes.
Yeah. Okay.
To some, I guess, ID prime.
All right. Yeah.
All right. So the message is written to the corresponding machine. I write new prime to say it has identity ID prime, whatever that is. And I have to say where it gets put, right? I have 3 tapes. So it's the input tape. The environment is giving input. And every message has to say where it comes from, with the sender as some external identity. So the idea is the environment is claiming to have one of the external identities, one of the identities that a main machine is a subroutine of. The environment doesn't say, I'm the environment. It says, I'm this external identity. Conceptually, you could think of this as saying, well, a C program running on, say, Linux could receive a message written to a socket. Maybe it has multiple sockets. Each of those sockets are an external identity. And when the operating system writes to the socket, it says, this was sent to this socket, even though it's the operating system doing the writing. It's the same idea here. So after we get this input tape, mu prime, the receiver, is going to run. Again, until it hits a transmit instruction. So that's if the environment is sending a message. Okay. If someone else is sending a message and the destination, right, the destination, ID prime, the person we're sending a message to, is external, right? It's one of the external identities. Then the message is written to the environment. The idea is this is the protocol is now responding to the operating system. It's giving some data to the environment as output. And crucially, this can happen at any point during execution, right? The protocol is interacting with the environment, not just in one big step, which was the problem with the last model. So it's written to the environment, output, so the environment is going to know both the sender and the external identity that it was sent to. ID is the sender's identity. And now the environment runs. So the first case is the environment giving input to the protocol. The second case is the protocol giving output to the environment, or possibly the adversary, right? Also giving output to the environment because it's just a not equals. Now the third case is some internal communication, right? In this case, a machine in the protocol is sending a message to another machine in the protocol. And if you're starting to lose me, that's okay. I'm going to go through a step-by-step example of how this execution runs. So if we're doing this internal communication, then the message is written to the receiver machine. It could be any label, right? It might be one machine calling a subroutine. It might be a subroutine outputting a value to its caller. So we don't set any particular label. We don't say specifically which tape it is. It's whatever tape the machine specifies. So the given tape and the ID, right? The receiver is going to know who sent it. And then the destination runs. And then finally, we could have a situation where a machine yields control. We'll see there's an instruction where it's possible that a machine stops executing but doesn't halt without transmitting data. And just to cover our bases, we say, if a machine...
Sorry, I did not process that.
It
can stop executing without halting. What?
Yes, it can yield. What will happen is it's possible that a machine can yield control, but it hasn't halted. It will run again at some point in the future. If that happens, we just define the environment to continue.
Okay.
So there are two things, right? There's yielding, which says I'm done for now, and there's halting, which says I'm done.
Mm-hmm. What's the difference between yielding and transmitting to someone with an empty string?
Yes. The difference is that if you transmit to someone with the empty string, then whoever you transmit to will get control next. Mm-hmm. If you simply yield, it goes to the environment. So I guess you could transmit to an external identity, right? But that's kind of a hack.
Sure. I can't tell what's a hack, but what is the environment? I mean, part of the Turing machine, part of the specification of the environment is some sort of rule for who gets to execute if somebody yields, or how do you determine the order of execution?
Yeah, so only one machine is ever running at a time. And the way this orchestration happens is the environment runs first. At some point, it transmits to a machine. then that machine runs. At some point, that machine either transmits to another, and then that machine runs, or it yields, in which case the environment gets control. And the way we define this semantics, and we will go back over this with a fine-tooth comb, there's only one way it can possibly continue. There's no sort of, there's no agency here, right? It has to go a certain particular way. There's no other way it could go.
Okay, then I'm happy.
In the third case, how is the tape specified?
Sorry, what do you mean?
So in the third case, how does the execution model know which tape?
Yes. So transmitting a message says which tape you're writing to.
Okay, yeah.
Yeah. So what might happen is an internal machine might say, now I'm going to call another machine, and it says transmit message to input tape of this identity. And then at some point that machine will provide output and it says transmit to my caller on the output tape. So that's specified in this instruction. Maybe I add a note here with on this tape. Does that make sense?
Yeah, that makes sense.
Okay, and the way that this execution finishes is the environment halting. When the environment halts, I'm making a bold statement here, it gives output. It gives some output. You can think of this as the environment has an output tape that eventually, when it halts, will have something written on it, possibly the empty string, possibly something else, okay? It gives some output, and we write, well, it gives some output. I'm going to abuse notation slightly here. I call it exec, parameterized by the protocol, the adversary, and the environment on input Z. And you can think of this as a random variable, right? These are probabilistic Turing machines. So their random tapes have some distribution. So you can think of the output as a particular value for a fixed set of machines in the support, or you can think of it as a random variable over the distributions of machines. Does that bit make sense? So the environment halts at some point, it spits out a value, and I'm going to call the value this, but it also represents a random variable.
Could you repeat what the randomness is in the okay, yeah, I hadn't been thinking about the randomness up until now. My mind just skipped it off the track. Okay, so we
don't need to worry too much about the randomness yet, but go on.
Yeah, okay, but I think I understand.
The idea is we need to plug in randomness at some point, right? Because if you want to encrypt something, I hope you're choosing the key randomly, right? It wouldn't be a very good key if it wasn't random. So randomness is going to have to plug in here at some point. And that will turn this output expression, this output thing that I write here, when we plug it in, that'll become a random variable. Okay, so I'm going to end the seminar today by just showing you how this little dance might play out in one particular case. And then next week, we'll return to this execution semantics and then look at it as a concrete model of computation. So let's imagine that we have, I'm going to draw things as nodes like a graph. We have the environment, we have mu1, we have mu2. These form the protocol, mu3. Which I will draw a box around them because they are the protocol. And I draw an edge to indicate that mu1 is a caller of mu2, and therefore mu2 is a subroutine of mu1. I won't draw both arrows because that will get ugly. But remember, this is a protocol, so it's got this nice closure property. And separately, we also have the adversary. And mu1 is the main machine, so I draw a dotted arrow to say it has an external identity that I will call ID. This is the external identity of protocol pi. Okay, so mu1 is the main machine, the others are internal machines, if you like. We've got the environment, we've got the adversary. So first thing that happens is the environment gets some input Z, okay? And the environment is going to run on Z, and at some point, it is going to say, now I want to transmit a value. So step 2 is the environment is going to, I drew this wrong, sorry. The environment is now going to say, I'm going to write to the protocol on its external identity. So the message, if you like, is, it says, on tape input, I send the message M to external identity, via external identity ID. Okay. Now mu1 is going to run, it's thinking, and now it says, okay, I'm going to give some input to mu2. Oops, it was too big. So step 3, I give some input to mu2. And this will look like input. I write M1 for the first message, and it's going to send, it was sent from identity ID1, right? When you're a machine, you receive some communication, you know who sent it. Okay? Now mu2 runs for a while, thinks about it, and let's say that mu2 is actually a corrupt machine. So it's now going to say, okay, I'm going to collude with the adversary. You could imagine this is some kind of, perhaps this is like a setup where you have a key server. Maybe the key server is compromised. Machine 1 is trying to get a key from the key server, and the server says, I'm going to talk to the adversary now to try to break the protocol. I'm just constructing a hypothetical scenario here. Okay, I chose my colors poorly, but that's okay. So now mu2 is going to talk to the adversary. And because it's talking to the adversary, this happens on the backdoor tape. And it's going to send some message, and the adversary knows who sent it. Now the adversary runs, it starts to think about it, and now it says, okay, I'm going to leak some information back to the environment, right? The adversary is allowed to talk to the environment, nothing wrong with that. I'm going to have to clean up this diagram a little bit. The lecture notes that I post on my website after this will have all of these stages laid out for you to peruse. So now the adversary at step 5 is going to send some information to the environment. Backdoor, M3, the adversary identity. Step 6. So now perhaps the adversary the adversary tells the environment this identity looked up a key. Machine 1 looked up a key. Okay, step 6. Now we're going to hand control back to the adversary. Maybe I say this is 6. I'm experimenting here with trying to make like active diagrams, so I apologize that I didn't entirely know what I was doing, but that's fine. So 1, 3.
Can I ask a question?
4,
what is
5.
What's left after this little loop through the environment? It's just the environment maybe recorded that fact on its tape somewhere.
Right, exactly. It's got it in its memory cell. It could in principle do anything now, but I say, okay, maybe it hands control back to the adversary. And now what happens next? The adversary, I'm going to stop drawing out all of this detail because it's getting in the way. And now the adversary says, okay, mu2, it's your turn to run again. That's, again, maybe I should have drawn this in purple. It's backdoor information. Okay, so that's backdoor information. And now, finally, mu2 says, okay, I can give me some output back to mu1. Maybe, some key that is biased in some particular way. And then, finally, mu1 does something and says, okay, I've done whatever it is that I needed to do, and I'm going to hand my information back to the environment via the external identity. And now, step 10, E halts and outputs, say, 0. So that's how the execution semantics works. The environment gets input. We have this little dance between different machines. Machines decide who to talk to. And at the end of the day, the environment is going to halt and output some value. It suffices to say that the environment only outputs a bit, but you could model more complicated things if you wanted. And the final statement that we want to make, definition 5, this is UC-emulation, but the restricted version, because we haven't gotten fully formal yet. The definition is that protocol pi UC-emulates phi if for all probabilistic polynomial time.
Phi is another protocol.
Yes. Protocol. If for all probabilistic polynomial time adversaries A, there exists a PPT simulator S, and S's job is to make the protocol pi look like protocol phi. So S is not adversarial. It's trying to, we want one that makes the two protocols look the same. Again, because if that's the case, then any attack that works in the real world works in the ideal world, and no attacks work in the ideal world, so we're good. Okay, such that for all BPT environments, one more layer, E, the maximum over all possible inputs of the probability that the execution of protocol pi with adversary A and environment E on Z equals 1. Say it's a bit. Minus the probability that the execution on protocol phi with the simulator and the same environment on the same input equals 1 is negligible in the length of the input. And that is the security statement that we will make fully formal starting next week. We go back to this distinction game, right? If the environment cannot tell the difference between the two worlds, in other words, it only outputs a different value with negligible probability, we say that the system emulates the target, and that is how we're going to phrase our guarantees. Okay, so important points today is this, trying to understand this dance that we've set up, that we have machines, we have the protocol that has a certain coherence property and can be called externally. We have the environment, we have the adversary, and we have this execution semantics. Air quote definition 4 is the most important thing going forward. Great. questions?
That's great. Thanks. I really got a lot out of that.
Cool. I'm glad to hear it. I recall a comment you made last week, right? That how are we going to wrestle a meaningful definition of this? This is how we're going to do it. And it's a little bit messy, but this is kind of, yeah.
Well, it's less ad hoc and messy than I was afraid it was going to be. It sort of mostly seems pretty natural. I still don't really understand when to call things backdoor and when to call them something else, I guess.
Yes. Yes, that's what I did. I did a little trick. I swept that under the rug. The details of what is allowed to be called backdoor information, the details of what the adversary is allowed to do. This is where a lot of the complication and subtle variance in definitions arise. But it's not too bad. But your instinct is correct that this is something that we will need to interrogate carefully. Just take my word for it. We need these things in order to express stuff without writing essays.
Good. Are there other questions? Adrian, did you have anything you wanted to ask them?
No, just a small technical question about the ninth, the diagram there.
Yep.
So communication between the environment and the mainframe, they don't use their own IDs, right? They use this other ID called the external.
Yep. So mu1, so when the environment calls mu1, it uses the external identity, not its own identity. When mu1 returns to the environment, it says that it writes to the external identity, and that is captured by definition 4 and routed to the environment. So as far as mu1 can tell, it's only interacting with its external identity.
Yeah.
But the environment obviously knows, that it's mu1 that it's talking to. So it's an asymmetric relationship. Actually, this reminds me of a technicality. Probabilistic polynomial time. Polynomial time in what exactly? That is a subtlety that we will have to be very careful with. It turns out to morally be polynomial in the length of the initial input, but it will get a little bit subtle when we get to that.
That's a good scary note to end on.
A cautionary tale, because defining polynomial timeness for interactive protocols is very, very difficult. Great. Okay, I'll leave it here then.
Yeah, thanks a lot. Look forward to next week.
Thanks, crew. See you next time.
See you next week.